Again, welcome back to calculus. In these lectures, we are going to learn how to find the derivatives of trigonometric functions. So we are going to start with three examples here. For example, we have a function f at x equal to 3 sine x minus 2 cos x. To find the derivative of this function, 3 sine x minus 2 cos x, is to know the derivative of sine x, and also we should know the derivative of cos x, which again we are going to cover the rules after this example. So the derivative, as we know, the constant value will be in the front, so we have the 3. Then the derivative of sine x will give us cos x. Minus 2, which is a constant value, derivative of cos x is minus sine x. So this is more or less like using the formula for derivative for trigonometric function. At the same time, this is using the difference rule and also using constant with the function rules. So again, we know 3 sine x, 3 is a constant value, so we leave it. Then we find the derivative of sine x, which will give us cos s. Minus 2 cos s, derivative of cos s is minus sine x. So our final answer will be 3 cos s plus 2 sine x, because minus times minus is positive. Now let's look at the second example. You can see, excuse me, the first example we use the difference rule, but we can see the second example here we are going to use the product rule, because we have h at theta equal to theta squared times sine theta. So here we have to use the product rule. So which means the derivative of h at theta will give us theta squared times the derivative of sine theta, which is cos theta, plus sine theta and the derivative of theta squared. So theta squared will give us 2 theta. So the answer will be theta squared times cos theta plus sine theta times 2 theta. Now theta is common in the two terms, so we bring theta out. Then we get a theta cos theta plus 2 sine theta. So we can see now we are using almost all the rules. Here we use the product rule with the trigonometric function formulas. Again, the first one we use the sum difference rules. Now let's look then. The next question, so we have to use again product rule, because we have sine theta times cos theta. We may also have a quotient example. For example, sine theta divided by cos theta. We know the formula for derivative of sine theta. We know the derivative of cos theta. So we apply the product rule. If it's quotient, we apply the quotient rule. So here we can say our answer will be sine theta times derivative of cos theta, which will be negative sine theta. So we get sine theta times negative sine theta plus the derivative of cos theta and then sine theta. And that gives us cos theta times cos theta, because the derivative of sine theta is cos theta. So sine theta times minus sine theta will give us minus sine theta squared. Cos theta times cos theta will give us cos theta squared. So our answer will be cos squared theta minus sine squared theta. And in trigonometric formula, cos squared theta minus sine squared theta is the same as cos 2 theta. So now let's go through the rules. So that's our first rule. We always can prove that the derivative of sine x is equal to cos x. So we have example here to find the derivative of y, which is equal to s squared sine x. So here we have to use the product rule again. So we can say s squared times the derivative of sine x, which will give us s squared cos theta, plus the derivative of s squared, which will give us 2s times the sine x. So our answer will be s squared times cos x plus 2x times sine x. Now the second rule is the derivative of cos x. So we know the derivative of sine x is cos x. Now the derivative of cos x is minus sine x. And that's the first rule here. The derivative of sine x is cos s. The derivative of cos s will be minus sine x. Then we can also find the derivative of tan x. But the best way to find the derivative of tan x, first of all, we know in trigonometric function, tan x is equal to sine x over cos x. So I can write the derivative of tan x to be the derivative of sine x divided by cos x. So here we have to use the quotient rule. We know the derivative of sine x will give us cos x. The derivative of cos x will give us minus sine x. But they are dividing, so we use the quotient rule. So we're going to get the derivative of sine x times cos x minus the derivative of cos x times sine x all over cos x squared. And that's what we have here. Then here we can evaluate it. So we get cos x times cos x minus sine x times minus sine x, which gives us cos square x plus sine square x over cos square x. So cos square x divided by cos square x will give us 1, or we cancel. Then sine x squared divided by cos x squared, we get what we call the sec. So here, what we are trying to say here is that cos x squared plus sine x squared over cos x squared will give us 1 over cos x squared. Why? Because cos x squared plus sine x squared is 1. So that's the best way to say it. Or I'm trying to say that we can differentiate, we can divide the equation into 2, cos x squared over cos x squared plus sine x squared over cos x squared. And that will still give us sec x squared, because we're going to get, again, 1 plus sine x squared over cos, but again, this is more straightforward. Cos x squared plus sine x squared is equal to 1. So we get 1 over cos x squared. And according to trigonometry, 1 over cos x squared is the same as sec x, sine square x. So this means the derivative of tan x always will be sec square x. So that's what we say, that the derivative of tan x is equal to sec square x. So here we say the derivative of the remaining trigonometric functions such as secant, cotangent, etc. can always be used. We can use the quotient rule to find them. Actually, the tan x, we use the quotient rule to find it. So that's the derivative of all the trigonometric functions. We should know, as we said, the derivative of sine x is cos x. The derivative of cos x is minus sine x. The derivative of tan x is sec square x. Now, the derivative of cosecant x will give us minus cosecant x cot x. Then the derivative of sec x will give us sec x tan x. Then the derivative of cot x will give us negatives cosecant x square x. So again, we can prove all this derivative of sec x, cotangent x, or cot x by using quotient rules also. So hopefully in the future we'll see more examples. So one example given here is we have an object which fastens to the end of a vertical spring as shown in the diagram here. And it can be stretched 4 centimeters beyond its resting position and also relates at a time equal to 0 as shown again. Now, its position at a time t is given as the following: s equal to f at t, which equal to 4 cos t. Now they say we should find the velocity and acceleration at time t and use them to analyze the motion of the object. Now, if a distance is given and you have to find the velocity, then we just have to find the first derivative. If we know the velocity and want to find the acceleration, we find the first derivative of the velocity. Or we can find the second derivative of the distance, and that will give us the acceleration. So let's see how we solve this problem. We start with the velocity. We say it's the derivative of what? The s dt. So we are looking for the derivative of the 4 cos t, because that's what is given here. The distance is 4 cos t. So velocity will be the first derivative. And here we have a constant value 4. So we find the derivative of cos t, which gives us minus sine t. So the answer will be minus 4 sine t. Now, to find the acceleration, we can find the derivative of the velocity, which was minus 4 sine t. Or we find the second derivative of the distance. So here we have the minus 4. Then the rate of sine t is cos t. So the answer will be minus 4 cos t. So here we can say that the object oscillates from the lowest point, s equal to 4 centimeters, to the highest point, s equal to negative 4 centimeters. We can see the value negative 4, previous negative 4. So the period of the oscillation is 2 pi, and the period of cos t. Now, as we said, the speed is v absolute. V always have to be a positive velocity. So it should be 4 sine t. Sine t have to be absolute value, which is greatest when sine t equal to 1. That is when cos t equal to 0. So the object moves faster as it passes through its equilibrium position, which is when s equal to 0. And also its speed is 0 when sine t equal to 0. That is at the high and low points. In terms of the acceleration, equal to negative 4 cos t, also equal to 0 when s is 0. And it has the greatest magnitude at high and low points, as we can see from the diagram. So we also have two special trigonometry limits. Improving the formula for derivative of a sine, we use these two special limits, which is limit theta approaches 0, sine theta over theta is 1. Also limit theta approaches 0, cos theta minus 1 over theta also is 0. These are very two special trigonometry limits. So let's see an example on this. So they say we should find the limit s approaches 0, sine 7x over 4x. So first of all, let's take the constant values. And so we say in order to apply the equation 5 we saw previously, we first rewrite the function by multiplying and dividing by 7. So sine 7x over 4x is equal to 7 over 4 sine 7x divided by 7x. Now, if we let the theta equal to 7x, and theta approaches 0, as x also approaches 0, we can have this equation. Limit s approaches 0 sine 7s over 4s will give us, again, 7 over 4. The limit s approaches 0 sine 7s over 7x. So this will give us 7 over 4, which is our constant value, times, again, 1. Here we get sine theta over theta, 7s. So final answer will be 7 over 4. So that will be the conclusion of these lectures. Again, in the future, we may see more trigonometric functions in our both derivative and also antiderivative. Again, thank you.